I'm recording now. All right, so I guess you're talking about this vector field here, which is, let's see, x y squared. What 1, I guess, plus x square, right? And then x square y 1 plus x square. All right. So you have to determine whether the given vector field is conservative. Which part you have trouble is to prove that it's conservative, or to find the potential?
So I found
so
first I integrate with respect to x, and then I derive with respect to y.
Mm-hmm.
And when I found the derivative, it wasn't equal to.
I mean, it's not supposed to be equal. Okay, let's.
Yeah, I know that. So then, because I didn't know what it was supposed to be, because I know that because. Okay, let me tell you what I got.
I mean, okay.
I got.
I
got
okay.
negative.
Let me go over the problem. So, okay, let me. So this is okay. So this is supposed to be derivative of f with respect to x, right? And this is derivative of f with respect to y. So you integrated the first equation with respect to x, I guess, right?
Yeah.
So you integrate this. So you integrated this. Sorry. So so this is x y squared plus 1 x squared. So I guess probably it's better to write this like x y squared and move this to the top. So 1 plus x squared to the negative 2. Anyway, so you have to integrate this with respect to x. Did you have trouble with the integration here?
No, I got
no. Okay. So I guess,
y squared over 2.
Yeah. So it's a substitution. So this should be your u, right? So I would say you would get 1 plus x squared to the negative 3. I need to divide by negative 3. And what do I need to do is also to divide by 2 times y squared. All right, so let me see. So this works. So derivative negative 3, sorry, minus 1 here. Sorry. This is negative 1. Oops. Negative 1 here. So you derive negative 1 plus constant. So that will be negative minus, let's say, y squared here, and 2 1 plus x squared plus c. Is that your answer?
Yes.
Okay.
We got.
Okay. So now, then I derived it.
Yeah, you derive it with respect to y. Okay. So you derive with respect to y. So that will be, so this is now f of xy. So derivative with respect to y. Of course, the denominator would be just constant. So that's just minus 2y. 2, 1. But so this is, I think this is not conservative. If it's not conservative, then you cannot find potential function f. I think this is not conservative. Anyway, so this is.
I think
it is,
because when I found.
Yeah, the partial n, partial m was equal.
They were equal.
They were equal.
Yes.
Yeah.
Okay. Okay. So then.
It's just the scalar potential for f is pretty. It's a little complicated. There's no trick we can do it here, right? No.
Yeah, because it was multiplication, so I was wondering how do we get the.
No, sorry. Here I forgot. So this is, sorry. Here it's not plus constant, of course. This is a plus a function of y, right? This is plus a g of y.
Prime.
Because, so this is g prime of y, right? This is because when you integrate with respect to x, or we derive with respect to x, the y is supposed to be constant. So the constant here is not it's not just it's a function of y.
Okay.
So okay, did you forget this g of y, this function here of y?
No.
Okay, so this is supposed to be equal then, so plus, sorry, this is g of y. So here, this is supposed to be plus the derivative of g with respect to y. And this is supposed to be equal to x squared y 1 plus x squared. Of course, this 2 here cancel out, right?
Mhm.
All right. And
That's
so,
where I'm at. I'm wondering how to find g prime of y.
well, g prime of y is supposed to be the difference, but the thing is, g prime of y, it must be a function of y. If there's an x left, then there's a mistake somewhere. Then it's not, I guess it's not conservative, or there's something wrong. Okay, so I mean, g prime of y in this case would be equal. So what we are saying is that minus y over 1 plus x squared plus g prime of y. Let me see. Okay.
Yeah.
Oh no, actually it simplifies. Okay, that's good. No, it works.
We got to compare, right?
Excuse me.
We have to compare with the.
Oh yeah, we have to
the partial.
compare with the, yeah, we have to compare. This is supposed to be the derivative with respect to y. Yes, so we have to compare to this one here, the x squared y plus. So what we are saying is that the derivative here of this function f is supposed to be equal to the second component of the, this is the second component of the vector field, second component of the vector field. Okay, no, actually I see it. There's a constellation here because of g prime of y, that will be equal to x squared y 1 plus x squared. That's nice actually. Plus, right, y over 1 plus x squared. So what I'm saying, guys, is that this is supposed to be a function of x, of y. If there's an x left in the expression, then there is something wrong. Okay, and here it seems like there is an x left, but there's not, because if you, so this is a common denominator, right? So that's x squared y plus y over 1 plus x squared. So if you factor out, I mean, y is a common factor, obviously, factor out the y. So that's 1 plus x squared over 1 plus x squared. And you see now the 1 plus x squared cancel out. So the g prime of y is just equal to y. Yeah. And that makes sense, because if it's really conservative, then the function g must be only a function of y. Okay. And of course, then you integrate this with respect to y. This is just y squared over 2 plus constant. All right. And so we come back. So the answer would be, would be this. So that will be this function here, right? But then g of y turns out to be y squared over 2 plus constant. You see how it works? But again, the thing is, your function g must be a function only of y. If there's an x in the g of y or g prime of y, then it's not correct. It's a mistake somewhere, or it's not conservative.
Okay.
Does this make sense to you?
Yes.
Okay, perfect. And any other question? I mean,
yes, I have question.
Yes, Dave.
Question 2. I guess you want to call it problem 3.
Problem three. Problem
Yeah.
3.
I had that one.
A closed curve on the ellipse.
Oh, the 2.3.
2.3. Yes, 2.3.
I thought you said problem 3. Okay. problem 2. Actually, this is see. Okay, actually, you can just use one result we had, which says that you know, your vector field F, right? So you're supposed to prove in the first part of the problem, you're supposed to prove that F is a conservative, right? In 2.1. So you know from 2.1 that F is a conservative, right? This is from 0.1. I mean the first part of the problem. Okay, this is from, right? Oh, sorry, it's conservative.
Okay.
Okay. So when a vector field is conservative, it means that the vector field is path independent. Look, path independent line integral. Okay. And if it's path independent line integral, it means that it depends only on the value of the potential function at the initial and the terminal point. Okay. In other words, so if you have a path, you know, you have some path. Let's say the path that goes from A to B. Okay. So and you prove that F is conservative. So which means that F is, this vector field F is you know, the gradient of some function F, right? So now, so what you know is that so if you integrate, so let's say this is my path gamma, okay? It's just a random path. So then the line integral along gamma of F, okay? So you can say that this is just I mean, the gradient of F, the function F along gamma, all right? And because it's path independent line integral, it depends only on the value of this function at the terminal and the initial point. So it means that this is just equal to F of B minus F of A, right? Okay. Now, the thing is, if you have a closed, so in the 2.3, it says we have this simple closed curve, right, which is the ellipse. So if you have a closed curve, simple closed curve, right? So you know, you have this this is my closed ellipse or circle or whatever, okay? It's some simple closed curve. So if it's simple closed curve, if it's closed, it means that the initial point and the terminal point, they take one side, they are equal, right? So in some sense, the A is equal to B, right? The initial and terminal point, they are equal. They are the same point, right? So then if you use this formula here, so then if you have this vector line integral along this closed, so let's say this is a beta. So your beta is this is a closed simple curve. Anyway, so this is, well, again, you get F of B minus F of A, right? But the thing now is A is B, right? So this is just F of B minus F of B. So this is just 0. Okay. So this is like a general statement. So what we are saying is that if you have a conservative vector field and you have a simple closed curve, then the vector line integral of the vector field along this simple closed curve is just equal to 0. Okay, so this is very general. So you don't have to parameterize your curve. You don't have to do anything. You know it's going to be just 0 because it's closed. The curve is closed. So this is very general. So this is general fact.
It's like a general rule. If it's
General rule. Yeah,
closed,
it's general rule. Yes.
vector field is to 0. Okay.
So what we are saying is you have F conservative. This is very important, of course. You have alpha or gamma, closed simple curve. Then curve or path, then you know that this is always zero, just zero. Okay. This is like, yeah, it's a general rule, but it makes sense, right? Because you see, because the integral would be just f at the terminal point minus f at the initial point. But if the initial and terminal point are at the same point, then that would be just zero. Right?
So yeah, like you said, based on that, we can skip multiple steps to getting.
Yeah, yeah. I mean, of course, if you if you have a time to waste, then of course you can parameterize if you want the, your curve, do the usual, computations for a vector line integral. But I mean, you're gonna get, at the end of the day, you're gonna get zero.
Okay.
So the answer should be 0.
Yeah, it's just zero. Yeah, the answer is just zero. Yeah.
Is that the same thing for 2.2?
No, that's well, it's different. You see, because in 2.2, the path gamma, it's not closed, because you see in 2.2, if you compare, what's the term initial point in 2.2? So this is 2.2.
It goes from
So
point A to
the
point B,
initial,
but it's not closed, right?
yes,
Okay.
initial point. I mean, the time t is in the interval 0, 1, right? So at time t equal to 0, that's my initial point. When I say initial point, that's the first, first value of t in the interval. So what's the initial point? It's just a gamma of 0. So gamma of 0 is like, I don't know, let's see, it's 1, e to the 0, it's 1, e to the 2 times 0, it's also 1. So this is my a. That's the initial point. A terminal point, that's the last value of the t in the interval. So that's t times t equals to 1. So that would be gamma of 1. So what would be gamma of 1? Well, it's 1 squared plus 1, that's 2, e, and then e to the e squared, right? So this is my point B. And of course, here a is different from b, so which means that this path gamma is not closed, right? Because they're different. I mean, the a and b are just different points, so it's not closed. But you can still apply this formula here, right? So it's going to be f of b minus f of a. The f is the scalar potential, is the potential you found in the 2.1. So you got this potential in 2.1, and that's what you have to use here. It's f of b minus f of a. Okay, so here gamma is not closed. Gamma not closed. Is that does this make sense? So this is not closed. So of course, then the answer is not 0. I mean, not necessarily 0. Any other question, guys?
I had a problem 3. You don't have to solve, but if it's negative, then I did something wrong with the calculations, correct?
The answer is negative.
Yes.
You're saying no. I mean, it's possible that the answer is negative, because here the work done, it's actually it has a sign, the work here, because of the orientation, depending on the orientation. So if it's negative, it's fine. It's not supposed to be positive.
Okay.
Yeah. Other question, guys?
I think it's fine.
It's fine. Alicia?
Yeah.
I don't know if Eric or Visivolod, you guys have questions. Anyway, just let me know, right? Okay, so if there's no more questions, then let me continue with the area of surface. So I didn't assign a homework yesterday, guys, because well, we just finished the conservative vector field, and you had homework about conservative vector field. So on Tuesday we did the area of we talk about parameterization of surfaces, and we discussed the area of smooth surface. I think they had just one example. So today we're gonna have more examples of area of smooth surfaces, and then we're gonna discuss scalar scalar surface integral and vector surface integral. And then, yeah, so then I would assign new homework next week. All right, so yeah, so let's finish this area of the smooth surface. So let me just remind you the formula we had. So this is section 7.4. So this is area of smooth surface. Okay. Okay, so before recalling the formula, guys, let me just explain the difference again between. Remember, in the chapter 5, we use the double integral to compute the area of surfaces in R2, right? But the surfaces in R2 are just some elementary surfaces. So in chapter 5. Okay, we have the surfaces in R2. Actually, they are supposed to be elementary surfaces. So we had elementary surfaces in let's call this surface S. And so this is important. This is also another difference with what we are doing now. So in chapter 5, we had surfaces in the plane. Okay, and the surface is supposed to be elementary, right? Which means that your for example, your x is between two functions of y, but then y must be between two constants. Okay, so we had some restriction on the surface, so it has to be elementary, and it's in the plane. Okay, so which means that in the plane, so we are in the plane. Here is your plane, and we have some let's say some surface S here. Okay, and we said so the area of this surface S would be double integral over S of dA. Of course, this is dA. This is the element, the area element, right? Okay. So that's a double integral. So we use the double integral to compute the area of surfaces in the plane. Now, what we did on Tuesday is, so now we are interested in surfaces, not necessarily in the plane, but surfaces in the space. So on Tuesday, so we had smooth surface as in the space. So it's not necessarily just in the plane. It could be in the space. So in the space, it means that we have now like phi axis, right? The coordinates. So your surface S, it could be just some random, some surface in the. So this is some surface in the space. It could be in the plane XY, like this is X, this is Y. So it could be just some surface in the plane, in the XY plane, right? This is another surface here, which lies on the XY plane. But now what we are saying, we can also compute the area of some surface which lies in the space, not just in the XY plane, right? And so I think we had one example, but let me first remind you of the formula and how it works. So we said we need the parameterization phi. So phi. So let's say the surface S is parameterized parameterized by phi. So phi, we said it's a function from some region in R2 to R3, right? So phi of uv is equal to x is a function of 2 parameters, same for y, 2 parameters, and same for z. And we said actually we need this function phi, or this map phi, to be actually 1 to 1. Okay, we need this phi to be 1 to 1 and smooth. So we need phi to be 1 to 1. Okay, and smooth. Okay, except possibly, I mean, if you want to apply this formula for the area of the surface, so all you need is a phi to be 1 to 1 smooth, except possibly at the boundary of this region D. Boundary of T. Okay. So we said that the area of the surface S. So we proved that the area of the surface S is equal. So so we proved this formula, and so it's actually equal to the double. It's also double integral over the region D. Okay, of the norm of the cross product of this cross product of these two special tangent vectors, TU and TV. Okay, DU, DV. Okay, and this is one reason we need this phi, to be this surface S to be smooth, because of course we don't want this cross product to be 0. Remember, in order to be smooth, first, of course, the phi need to be 1 to 1, but then smooth means that this is not 0, right? This is not the 0 vector. Anyway, so we have this formula. So this is the area of our surface S, our smooth surface S. Now, I think we had just one example. Now let's have more examples. More examples. Okay, so I mean, on Tuesday we discussed the case when the surface S is the graph of some function f, function f of 2 variables. Remember, so we said the graph. So let's say we have a function f of 2 variables. So f is a function of x and y. Okay, so you have the function of 2 variables. Then the graph of f is, of course, is going to be a surface, right? Again, the idea here is that if you want to graph this function f of 2 variables, you're going to need a third axis, right? So this is like for a function of a single variable. For single variable f of x, then you want to graph f of x, you're going to need a second axis, which is the y-axis, right? And the graph would be y equals to f of x, right? Now, and here's your graph. Now we have this function f of 2 variables. So if you want to graph f, then you're going to need the z-axis. So we're going to graph f of x, y. So then z would be equal to f of x, y. Okay. And I mean, I guess I explained on Tuesday that the idea is that So here's X, here's Y, here's Z. So what you do is, so you have some XY here, a point here, let's say X0, Y0, right? And then, so by the function F, you're gonna associate its image, right? This is gonna be X0, Y0, F of X0, Y0, right? So what you do, guys, I mean, is that, so to each point of the XY plane, you know, you associate its image. So there's another point here, you associate its image, etc. So to each point of the plane, so think of that. I mean, to each point of the plane, you're gonna associate an image, right? And so then the set of the images will be some surface S. Okay. So in other words, what you are doing is like, again, it's like twisting the XY plane using this function F, right? So the image of the XY plane by the function F would be some, you know, twisted plane in some sense. And that would be a surface. Anyway, so we said, how do we parameterize the graph of, so this is a surface, of course. The graph of f of x is a surface. So how do we parameterize such a surface? So, well, the simplest way, of course, to parameterize a surface given by the graph of some function f is just to say, so how do we parameterize z equals to f of xy? All right, so this is phi uv. You know, the first coordinate here, first component here is supposed to be x. This is supposed to be y, and this is supposed to be z. So you see the graph, the surface S is given by this equation, right? Z is equal to f of xy. So that's like the only restriction you have on your variables. Your z coordinate must be equal to f of xy. So what we can say is that the variable x is just some random variable. There's no restriction on x, could be any number. So let's say x is a parameter u. The same for y, there's no restriction on y. So, and it's not really related to x. Okay. So in some sense, it's an independent variable, right? So then y is equal to v. Now, the z, there is a restriction on z. And the restriction is this one here. Z must be equal to f of xy. Right? So this must be equal to f of xy, but we said x is u. So that will be f of, and y is v. So that will be f of uv. Right? So you see, guys, how I parameterize the graph of this function f of xy. That's the simplest way to, of course. There are infinite ways, of course, to parameterize the surface, but this would be like the simplest way to parameterize this the graph of this function f. Anyway, now you want to compute, let's say, you know, the area of the surface. Well, as I said, in theory, you need to check that this parameterization is 1-to-1. Okay, and it's the case here because here, mark here. I mean, this phi is 1-to-1 because, so if 2 points that have the same image, so because if, you know, if a phi of u1 v1 is equal to phi of u2 v2, so 2 points they have the same image, then what's phi of u1 v1? It's supposed to be u1 v1 and f of u1 v1, right? So the hypothesis here is that this is equal to phi of u2 v2, which is u2 v2 and then f of u2 v2, right? But then if these two points are equal, so then you know, the first component here is equal to this first component, and the second point here, v1 would be also equal to v2. So the conclusion is that, so then u1 v1 is equal to u2 v2. Okay. So if 2 points they have the same image, then the 2 points are equal. Then the u1 v1 is equal to u2 v2. So this map is 1-to-1. Okay, so this is 1-to-1. Okay, so now, is it smooth? Right? Well, we just we can check. Let's check if it's smooth. So is it smooth? Well, you just compute the, as usual, you compute the, so this is phi of uv. Again, it's uv, phi of uv. Of course, you need this function f to be differentiable. I mean, the derivative to exist. But then t subscript u, that's the derivative with respect to u, so that will be equal to the vector 1, 0, partial f, partial u, right? Then t v, that will be 0, 1, partial f, partial v, right? And so tu cross tv, and so the cross product of the two vectors, that will be equal to, please guys, again, if you have trouble with cross product, just let me know. So that will be equal to, so you cross multiply here. So that's minus partial f, partial u. And then you cross product, cross multiply here. Sorry, I should use a different color. This is supposed to be like this. So it's minus partial f, partial v. And finally, red here, this is just equal to 1. So here's 1. And of course, this is it's never 0, right? Because I mean, the last component, it's 1, so it's never, this is never 0, right? So which means that the graph, so what we are saying here, guys, is that the graph of function f, again, you need the function f, of course, to be differentiable because you need the derivative to exist. But the conclusion here, of course, is that the graph of the surface given by the graph of some function f is it's always smooth everywhere, right? So so the graph of f of xy is smooth everywhere. Okay, so now we can compute the area of the surface, or the area of this graph. So that will be just equal to, so we need, so the question now is, what's the area of the graph? The area of the surface in this case. Well, we are supposed to compute, you know, the norm of tu cross tv. Okay, so that will be equal to, so here's the components of tu cross tv, right? So then the norm, or the magnitude of the vector, would be the square root of the square of the first component plus the square of the second component plus the square of the third component, right? So this would be square root of first component, square of the first, square of the second component, plus square of the third component, which is 1. Right. So what we are saying here, so we have like sort of general, very general formula here. So the conclusion is that so the area of a graph so there'll be a double integral over the region D, of course, of this, the norm of this vector, tu cross tv. So that's square root of, you know, derivative of f with respect to, let's say, u square plus derivative of f with respect to v square plus 1 du dv, of course, here, du dv. Right. Okay, so this is very it's a very general formula. So let me just give you a numerical example, and then I will give you an exercise. Okay, so an example, numerical example. Oops. So guys, in the homework or the test or whatever, if you have the graph of some function f, and you want to compute the area of the surface, you don't need to do all these computations, all right? So you can just apply this this formula right here. Okay, this one here. Okay, so for example, numerical example, let's say you want to find the area of the paraboloid. So find the area of the paraboloid let's say so f of x y equal to 9 minus x squared minus y squared, that lies over the xy plane. Okay. Okay, so what's this paraboloid that lies over the xy plane? Well, so oops, here. So lies over the xy plane. It means that, of course, let's say let z equal to f of xy. So z is equal to 9 minus x squared minus y squared. So the lies over the xy plane means that the height z must be positive or 0. Okay, so this must be positive or 0. So if you want to graph this, so this is x, this is y, here's my height z. So actually the vertex of this paraboloid, so when x and y, so when x and y are both 0, then the height z would be 9, and that would be like the highest point of the this 9 here. So that would be like the highest point of your paraboloid, right? So it's 9 minus x squared minus y squared, which means that this paraboloid actually it opens down, okay? Because, well, I mean, you're gonna subtract minus x squared minus y squared, so you're gonna subtract positive numbers from 9, so which means that the height z is gonna decrease, right? If you subtract positive numbers, x squared, y squared are positive, right? You subtract positive numbers from 9, so then the height z would decrease. So this paraboloid would be just like something like something like this here. Okay, so this is 9 minus x squared minus y squared. And again, it lies over the xy plane, right? So we the height z must be larger or equal to 0. Okay, let me just make one comment here, guys. Like, so what we did in chapter 5, like in this case, we would be able to, for example, compute the volume of this, the volume of the interior of this paraboloid, right? So like in chapter 5, what we did is, so we'd be able to compute the volume of the interior of this paraboloid. So then the volume of the interior of this paraboloid would be equal to interior of the paraboloid would be equal to the triple integral of 1, of course, volume element over your paraboloid here. Okay. So in chapter 5, we'll be able to compute the volume of the interior of this paraboloid, right? So now what we are doing, we are computing the area of the paraboloid. It's not the volume of the interior. We are computing the boundary in some sense, the boundary of this interior, right? We are computing the area of the paraboloid itself, not the volume of the interior. Okay, so now, so now what we can do is, now we can compute the area of the boundary of this solid, so the paraboloid itself. Okay, so these are two different things, right? The volume. Sorry, guys, I forgot to turn off my phone, I guess. Okay. Just 1 second. Sorry, I'm just turned off my phone. Hello. Sure. Okay. Perfect. Sorry, guys. That's what happens when you when you stay at home. Yeah. So, well, I hope you see the difference, right, between the two things, right? The volume of the interior and the area of the paraboloid itself, right? All right. So, okay, so what will be the area in this case? Well, all we have to do, guys, is just to apply our formula. So our formula says that the area of this, so the area of this paraboloid, so it will be double integral the region D, and we said, so this is a graph, right? It's given by, so this surface is given by the graph of this function f, right? This one here, right? So we can just use this formula right here. So then the area of the graph in this case, so double integral of square root of 1 plus, derivative of f with respect to u plus derivative of f, the square of the derivative of f with respect to u plus the square of derivative of f with respect to v, etc. Right? So this is just equal to, so square root 1 plus derivative of f with respect to u, x, plus the square derivative of f with respect to v, right? du dv. Okay, guys. Now, so what's f? F of, well, I mean, f of xy, it's 9 minus x squared minus y squared. I mean, if you write this in terms of u and v, is just 9 minus u squared minus v squared, right? So this, the area would be equal to, so over the region D, so this is square root of 1 plus, so derivative of f with respect to u, that will be a minus 2u, so this is minus 2u squared, right? And plus derivative of f with respect to v, that will be minus 2v squared du dv, right? Now, what about the bounds of du dv? So this is du dv, so u and v, I mean, or x and y, right? Because u is x and v is y. So, you know, x and y, so x and y, they're supposed to be, so you can see here, right? So my x and y, they are just in this circle of radius. So this is, you know, when z is 0. So 9 minus x squared minus y squared is equal to 0. So in other words, x squared plus y squared is equal to 9. Okay. Or if you prefer, that's u squared plus v squared equals to 9. Okay. So what I'm saying is that the u and v, they are just in this circle of radius 3, right? So here, the region is D is just this is just the circle, interior of the circle. So this is the disk. So u plus v squared less or equal to 9. Okay. Anyway, so this is actually equal to double integral square root of 1 plus 4u squared plus 4v squared du dv. And here we have u squared plus v squared less or equal to 9. So, of course, here you're going to have a little bit trouble or problem to compute this integral. So the idea, of course, would be to use, because we have you see the region here, it's just u squared plus v squared less or equal to 9. So that will be the interior of the circle. So the idea would be to use, of course, polar coordinates to compute this integral. Right? So if you use polar coordinates, so then that will be equal to double integral. So u is, let's say, r cosine of theta, v is r sine of theta, right? So u squared plus v squared less or equal to 9 means that your radius r is between 0 and 3, right? And theta is just 0 and 2 pi. Here, this is square root of 1 plus, so you can factor out the 4, that's 4 u squared plus v squared, and of course u squared plus v squared, that's r squared, right? U squared plus v squared is just r squared. So this is 1 plus 4 r squared, and then don't forget for the Jacobian du dv polar coordinates, there'll be r dr d theta. All right. And then this is not really hard to integrate because you can just use a substitution. You can say, well, this thing here is my, use substitution here. Let's say this is u is 1 plus r, 1 plus 4 r squared, right? So, then the integral would be just, let's see. So du, of course, would be 8r. And so the integral here would be 1 plus 4r squared to the power, I guess, it's half. So this is power 3 over 2. So you need to divide here by, the reciprocal. So that's a 2/3. And what do you need else? Derivative of it's 8r. There's an r here, so you need to divide by 8 here, I think. Okay. And r between 0 and 3, d theta. Anyway, does this make sense to you guys? I mean, just let me know if you have any questions. Just stop me, right? And then, okay, so this is just evaluation here. I mean, let's see. So you integrate with this to theta. That's just 2 pi This is 2/8. That'll be 4 here. That's 1/12. This is 1/12. And then 1 plus, r squared, that's 9. 9 times 4, that's 36 times 3 squared here to the power 3 halves, and then minus r0, so that'll be just 1. Okay. Anyway, so that will be the answer. Let me just say, guys, here in this case, the area, it must be positive, okay? Because area, it's just must be positive, okay? Is there any question, guys, about this example?
No.
No. All right. Yeah, but I mean, just keep in mind the difference with what we did in chapter 5. Chapter 5 would be able to compute the volume of the interior of the paraboloid, right? Now we are computing the area of the paraboloid itself, okay? That's the difference with what we did in the chapter 5, with double and triple and double integrals. Okay, here's an exercise for you guys. Exercise. So let's say, so here's a parameterization phi. So S surface is given by phi. So phi of UV, let's say, is equal to, let's see, let's say 1 or 1 plus cosine of V times cosine of U, 1 plus cosine of V again, sine of U, and then sine of V. So let's say U here is U and V both are between 0 and 2 pi. So U between 0 and 2 pi, and same for V between 0 and 2 pi. All right. Okay, so this is a parameterization of my surface S. So the question is to compute the area of the surface S. Okay. So again, the formula, just remind you of the formula. So the formula says that this would be, the formula is the following. So we have this parameterization. Once you have the parameterization, then you can compute the area. So the area would be this double integral D. So like here, D would be, that's the region of, the U and V. So U is between 0 and 2 pi, V is between 0 and 2 pi. So this is double integral of T, the norm of TU cross TV, du dv. Okay, guys, I'm gonna give you, let's say, 5 minutes to think about this problem. I'm not sure I'm gonna go over this problem because it's gonna be a long computations, I guess. I'm not sure. But anyway, so I'm gonna give you first 5 minutes to think about this. So the steps are, of course, let me just say here. So I would say the main step is to compute this T subscript U cross T subscript V, right? Compute the norm, and you can also try to check if this parameterization is, you need to, as I said, you need this parameterization to be 1-to-1, and also smooth. Okay, you can try to check that if you want, but that would be a lot of, I guess, a lot of computation. So my suggestion, guys, just to try to apply this formula. Okay, just try to apply this formula, and that'll be fine. So again, this is different from my previous example. The previous example, I mean, the surface was given by the graph of some function f. Here, the surface S is not given by a graph of a function. We have the, we have the parameterization of the surface S, but it's not given by the graph of some function f. I think I have the answer. What's the answer to this? I think the answer would be 4 pi squared. Anyway, guys, so let me probably just give you the answer because again, the computation is kind of long. You have to compute derivatives, then you have to compute the cross product. You have to simplify your cross product. So I claim that if you simplify your cross product, then so the answer here. Oops. Again, I won't do the derivatives and the etc. because it's just a long, kind of long computation. So the answer here, well, at least for the cross product, so your cross product should be equal to, I mean, if you do TU cross TV, this is, if I am not, of course, if I'm not mistaken, this should be equal. After simplification, you have to use the trig identity, cosine square plus sine square, I think probably twice. But if you simplify using trig identities, then this would be equal to, the norm of this thing here. The norm. So this is after simplification, of course. Simplification. This would be equal to 1 plus cosine of v. Okay. I don't know if you guys got this answer. or probably you didn't have time to compute this thing here. But anyway, so again, if I'm not mistaken, the length, the magnitude of the cross product would be equal to 1 plus cosine v, and then the area in this case would be, so the d here, u and v, both are between 0 and 2 pi. So here we're going to have like 0 to pi, 0 to pi. The magnitude of your cross product, that's 1 plus cosine of v, okay? And then du dv, okay? So, I mean, this is very, it's not really hard to integrate. And so the answer should be 4 pi squared. Okay. Anyway, and that's, of course, it's positive, right? 4 pi squared is positive. All right, guys. Do you have any question about this area of surfaces? But I hope you understand again the difference with what we did in chapter 5. I mean, it's really important that you distinguish between what we did in chapter 5, which was the double integral, the area of elementary surface in the plane, and what we are doing now, which is the area of a smooth surface in the space, not necessarily in the plane. Okay. All right, guys. If there's no questions about this areas thing, so it's going to be, of course, in the homework. Anyway, I hope these examples that would help a little bit. So now we're going to move to the surface integrals. So we're going to move to the section. So probably I can move to a new page. So yeah, so this would be section 7.5 plus 7.6. So we're gonna do the scalar surface integral and the vector surface integral. Okay, this is very similar to what we did with the paths, right? The line integrals. We had a scalar line integral, and we had a vector line integral, right? We integrated functions, and we integrated the vector fields. So we're gonna do the same. So this is a surface integrals. So the goal here in this section, the goal is to learn how to integrate functions. So here functions, they are the range of the functions here are R. So that's what I call the scalar valued functions. This is a scalar valued functions. So again, scalar valued functions means that the function here f, so the function here f, it's it goes from some domain to R. So the result, the answer should be a number, so some real number. So that's what I call a scalar valued functions. And of course, vector fields along surfaces in the space in R3. Okay, in R3. Again, this is analog to what we did for along integrals along paths, right? So let's start first with the scalar surface integral. So let's say you have some surface in R3 in the space as some bounded surface in R3. All right, and let's say you have some function f, a scalar value function f. So let f is a function. So we are in the space, so function of three variables, x, y, z. We need f, of course, to be actually continuous. Some continuous function. Whose domain includes of course, the surface S. Anyway, so let's say this surface S is parameterized by, by phi, parameterized by so phi here, so some region in R2 to R3. Again, we have, phi of uv as usual. That's x of uv, y of uv, and z of uv, right? Okay. Then we define, the scalar surface integral. So we're going to integrate this function f along this surface S, right? Again, like for paths, we integrate functions along paths. So here we are integrating functions along surfaces in the plane. Sorry, in the space. So the scalar surface integral. So the definition is the following. So of course it's the integral. It's the integral of f. Oops, along the surface S. So here's my function f along the surface S. Again, S is the surface in the space, and of course here we integrate with respect to here. We're gonna need the area element of the surface S, right? This is the area element. So what's the area element of the surface S of S? So remember, guys, what's the area element? So by definition, when you integrate the constant function 1 with respect to the area element, then the double integral would be equal to the area of the surface S, right? So just remind you that, the area of the surface S, if you suppose, of course, suppose that your parameterization phi is 1-to-1, and smooth except at the boundary of the region D. But then the area of the surface S would be just the double integral over S of your area element, right? But the area element is, so the area element would be this norm of the cross product du dv. That's my area element in this case. Okay, so my area element in this case, when we have a parameterized surface, is this the norm of this cross product du dv, right? And that's actually what we proved on Tuesday. So on Tuesday, I showed you guys why the area of a very small, let's say, parallelogram which lies on the surface S is equal to this norm of this cross product, right? Anyway, so this would be equal to, so by definition, so this would be equal to, of course, double integral of f. So it's along the surface S, which means that the x is equal to x uv. Y is equal to y uv, and z is z of uv. This is a function f, so it's f of x uv. It's along the surface S. So here it's going to be over the region D, y of uv, z of uv, and then of course times the norm, it's with respect to the area element, which is the norm of TU cross TV, okay, DU, DV. Okay, so here, guys, again, this dot here, this is multiplication of functions. Okay, just multiplication of product of functions. This is product of functions. Okay, f is a function. This norm, this norm here, or the magnitude of cross product, it's also a function. Okay. Okay, so before the examples, guys, I mean, what would be an interpretation of this scalar surface integral? So you should think of this scalar surface integral as the, this is your area element, all right, of the surface S. So what we are saying is that, you have your surface S. So here's the idea here. Okay, so we have our surface S. This is my surface S, right, etc. And this dA would represent, so you have a small, let's say a small parallelogram here. This is surface S. So the area of this thing here, this very small, let's say parallelogram, is equal to this, the norm of TU cross TV. Okay, of course, at some point here, you fix a point here. Let's say the point, this is the point P. For example, this is the point, P, which is phi of some U0, V0, right? So what I'm saying is that the area of this small parallelogram with the vertex at point P is equal to this function here, this norm of the cross product at the point P. Okay, so you're going to get some number. Anyway, so what we are doing here is we are multiplying the area of this small parallelogram with this function f, right? So function f, it's function defined, it's along the surface. So you have, this is your point P, right? So this is U0, V0. So you're going to multiply by, so this is, let's say, this is the f of, f of P. F of the point P. Okay. So when you multiply, you're gonna get, so if you multiply this area of this small parallelogram with this f of P, which is sort of weight, or like, let's say this is like the height, right? So you're gonna get the volume of this parallelepiped, right? This one here. And of course, you do the same for all like small parallelograms here. There's another small parallelogram here. You do the same thing times this function f. Well, let's say in this case here, f of P, or f the function f here at the point P would be, let's say, kind of smaller, right? So you're gonna get a smaller volume, let's say, okay, etc., etc. So you can imagine, you do the same thing for each very small parallelogram. You multiply by this function f, okay, and so you can think of this integral. So integral, of course, when you say integral, we say Riemann sum. So it's a limit of some Riemann sum. So integral, this integral here, this is scalar surface integral, okay, along S. So you can think of this as the limit. So this is the limit of a weighted sum. Weighted sum. So of course, so you have the sum of all these the volume of all these parallelepipeds, right? So if weighted sum of the surface, the area or of the surface area pieces times times the weight here would be your function f times the weight f here, so times the weight f. Okay. So again, you do the same for each very small parallelogram, and then you take the limit. So here's another small parallelogram, here's another small parallelogram. You multiply by the function f. Here at some point at this vertex, you're gonna get this parallelepiped here, same thing here, etc., etc. Right? All right. Any question, guys? Again, this is just the sort of interpretation of this scalar surface integral, right? Again, the idea is the same like for, if I have a function of single variable, f of x dx. This is just, so what you do, you have your interval. So you divide your interval in very small into very small sub-intervals. And you multiply by the function f at let's say some point of your interval. So you're gonna get, let's say this rectangle here. Here is another rectangle, right? This is just a function f here, function f, and so this integral, for the integral of this single variable, that will be the limit of the sum of all these small rectangles, right? And so the idea here is just the same. It's just instead of small intervals or sub-intervals, we have now like a small, let's say, small parallelograms. Okay. Any question, guys, about this scalar surface integral? Anyway, so that's roughly speaking, that's the idea. Now, here's an example, numerical example. Let's say you want to evaluate the double integral along the surface S of the function z cube, okay, where S is, let's say it's the sphere of radius 1. Okay. So my function f here, it's just the function z cube, right? My f of xyz, so this is my function f. This is f of xyz. Okay, so f of xyz is just equal to z cube. All right, so you want to integrate this function f along my surface S, which is the sphere of radius 1. All right, so again, for this formula here, for this scalar surface integral, you don't really need the parameterization to be 1-to-1. Okay, in case that the parameterization is 1-to-1 and smooth, then if you integrate, for example, the constant function 1, that would be the area. But in general, I mean, for this scalar surface integral, you don't need the parameterization to be to be 1-to-1 or smooth. Okay. Anyway, so all right. So how do we parameterize the sphere? I mean, we have seen this like probably last week or probably 2 weeks ago. I'm not sure. I think the last week. So for the sphere, we can parameterize the sphere as follows. So we can say cosine of u, sine of v. I think it was sine of u. Sorry, sine of u, sine of v, and then cosine of v. Okay. So again, the idea is that this is your x, this is your y, this is your z, and if you do x squared plus y squared plus z squared, that'll be equal to 1, right? So if you do x squared plus y squared plus z squared equals to 1, the u is between 0 and 2 pi, and v between 0 and 2 pi, so 0 and pi. All right. And actually, we discussed this probably on Tuesday or last week, and we said this is actually 1-to-1, except it's 1-to-1, except at v equals to 0 and pi. Okay, so it's actually 1-to-1 everywhere except at the when v is 0 and pi. Anyway, so if you want to, again, I mean, it doesn't matter if it's 1-to-1 everywhere or not. You can always evaluate this scalar line integral. Sorry, scalar surface integral. All right, so how do we do that? Well, the formula says the following. So this is supposed to be equal. So the formula says that this is this integral of this function z cubed. S. This is a double integral. So I need to express this function z along the surface S. So along the surface S, as z is equal to my z coordinate is equal to cosine of v, right? So my z coordinate is cosine of v. Okay, so here we're gonna have cosine of v cube, right? But because again, the z coordinate, because of the you are using the parameterization, right? In the parameterization, the z coordinate is equal to cosine of v. So along S, the z is cosine of v. All right. And now there's this area element, which is we said this is equal to, of course, the norm of tu cross tv du dv. U, of course, where is it? U is between 0 and 2 pi, right? And V is between 0 and pi. So U is between 0 and 2 pi, and V is between 0 and pi. Okay. So all you have to do, guys, now, of course, is to compute this, the magnitude of this cross product. I mean, we did this a couple of times, I think. Again, I won't do the derivatives because we did it at least once. So let me just say that when you do the cross product and take the length of the cross product, then that will be equal to sine of v. Okay. Again, we did this, I think, on Tuesday or for the sphere. We had similar computations like on Tuesday or last week. Okay, this was done before. All right. Anyway, so this thing here turns out to be sine of v. Okay, so my scalar. So my scalar surface integral is just so 0 pi, 0 2 pi, cosine cube v times sine of v du dv. So I mean, this is just in terms of v. There's no u. Okay, so that will be equal to. So if you integrate with respect to u, that will be equal to. So u is between 0 2 pi, so that'll be 2 pi, and then you're gonna have 0 pi cosine cube of v sine of v dv. Okay, now we integrate this with respect to v. This is just you can use substitution here. So this is so u here. Let's say u is not u. I need to take out to use another parameter, I guess. Substitution. So let's say this is substitution. Let's say substitution. Let's say w. Okay. Equal to let's say w is cosine of v, right? And of course, you know, dw derivative of cosine of v with minus sine of v dv. Right. Anyway, so use the substitution, guys, and then so the answer would be, so the integral would be here 2 pi times. So we're gonna have minus cosine to the power 4 of v over 4, evaluated between 0 and pi, right? And so cosine of pi is -1, -1/4, that's +1, so -1, and then -1 plus +1, that would be 0. So the answer here would be 0. Okay, final answer. Any question, guys? All right, so here's an exercise for you. I'm going to give you a couple of scalar surface integrals to evaluate. Exercise. Let's say the surface S is the cylinder. So this is, it's parameterized by phi uv, phi cosine of u, phi sine of u, v. The u, the angle u is between 0 and 2 pi as usual. V, let's say, so we're gonna take the cylinder. So of course here you see, guys, this is supposed to be your x, this is y, this is z, and if you do x squared plus y squared, you're gonna have 9. So which means you're gonna have the cylinder along the z axis. So you're gonna have the cylinder, you know, you have here's the circles, x squared plus y squared equals to 9. So you're gonna have the cylinder here along the z axis. Then we're gonna, because you need the surface to be bounded, right? So the v, let's say the v is between 0 and 15, okay? So we're gonna take the portion of the cylinder which is between, you know, height z between 0 and 15, okay? Z is equal to v, so the height z is between 0 and 15. All right, so the question, guys, is to evaluate, let's say, so the scalar surface integral of the function z along the surface S. Again, S is a portion of the cylinder along the z-axis between 0 and 15. Exercises, so exercise number 2, this is 1, 2. For number 2, let's say S is the graph. So I'm gonna take again the paraboloid. Z 4 minus x squared minus y squared. Okay, the x squared, y squared. So with x squared plus y squared less or equal to 4. Okay. So in other words, the z is positive here, or 0. So the z here is larger or equal to 0. Okay. So in other words, this would be this paraboloid here. So the top would be when x is 0, y is 0. So the top would be 4. So we have 4 here. And So here's the circle, x squared plus y squared equal to 4. Okay, so this is just a x squared plus y squared equals to 4. This is when the height z equal to 0. Anyway, so that's my paraboloid. Again, it lies over the xy plane. So that's my surface. And so what you have to evaluate, guys, so please try to evaluate double integral or log s of, let's say, 4 times 4 minus z plus 1. Okay. Of course, you wonder why I wrote this like this plus 1. I mean, I can write like a 17 minus 4z, but you will see this makes probably the allows you to actually to easily compute your integral. Okay. Anyway, okay, so let's say, guys, you have only 9 minutes. So I'm gonna give you a couple of minutes to think about these 2 exercises. I don't know if probably I would have just time to go over the first, and yeah, and then next time we will do of course the vector surface entry. Okay, guys, I'm gonna give you a couple of minutes to think at least about the first problem. I forgot to zoom out. Zoom. No. Zoom in here better. All right. Okay, guys. Let me just remind you guys again the second test. Just remind you that the second test is gonna be on May 11th. If I'm not, let me see, check my calendar. Second test, where is it? Yes, yeah, May 11th. So it's May 11th. Final, it's May 25th. So final, again, it starts at 9 a.m. This is really important. It's a 3 hours exam. It starts at 9 a.m. It's not at 10 a.m. It's at 9. What else I'm gonna say? Yeah, and of course we're gonna have a review just after the second review for the final, just right after the second test. Okay, and please, guys, don't forget, of course, your homework, which is due today, homework number 5, and next week I will assign the new homework as usual. Oh yeah, I forgot. I want to advertise for this undergrad research program. It's called the LSAM. So it's actually you get paid like 3,000, I think, $3,000. So the idea, of course, is to work on some project with your professor. It's not necessarily connected to your courses. It's something you decide with your professor, right? And it's actually for 2 semesters. Okay, it's not just for 1 semester; it's for 2 semesters. Okay, but it's again, it's you get paid $3,000, which is not bad, and it's really good for you guys. I mean, if you have time, that's a good idea to do some undergrad research program, because it's for your CV. I mean, later, I guess it will be really important for you to have some, some undergrad research project. So, yeah. Anyway, you can find the details on CUNY Blackboard. There's a link there, and if you click on the link, you have the the form you have to submit, so you can apply to this program. And yeah, anyway, if you have any question about the program, just let me know. So let me just say, guys, what will be the plan for next a couple of weeks. So I mean, the last day of classes, it's supposed to be, I think it's May 17th, right? But it's a Monday. So I think our last class would be the one on 13th. Okay, that will be the last class. This one here. This would be the last class. So anyway, so we have like well, it's approximately, let's say, 2 weeks and a half or 3 weeks left, right? I would say 2 weeks because well, we're gonna have a test, we're gonna have a review, so that's not really it's not really lectures. But the plan, guys. So after the vector surface integral, again, it's kind of very similar to this scalar surface integral. I'm gonna discuss a little bit about the reparameterization of surfaces. This is exactly analog to what we did for paths, right? Remember the reparameterization of paths? It's the same thing for surfaces. A surface has infinite number of ways to parameterize a surface, and we will see that that this first the scalar surface integral or the vector surface integral is independent of the reparameterization, but it depends only on there's a orientation on the surface. So I'm going to talk a little bit about the orientation of surfaces. But if you have opposite orientation, you're gonna have opposite opposite integral. But otherwise, it's independent of the reparameterization. Okay, and then I'm going to talk about the Stokes-Green's theorem. Again, this is just a generalization of sorry, not the Green's, but Gauss divergence theorem. So Stokes-Gauss divergence theorem, generalization of Green's theorem to the space. That will take probably 1 week, and then there'll be 1 week left, or probably 10 days left. And then the last week, I'm gonna talk a little bit about differential forms. Differential forms is kind of an very advanced subject, but I'm gonna just really just introduce differential forms. Differential forms, they are in your, for example, area element or volume element or length element. They are just the differential forms. So I'm going to talk a little bit differential forms, and I wish if we still have time, I'm going to talk about some applications of this, what we are doing now, the parameterization of surfaces. I'm going to talk about the curvature of a surface. So I guess in Calc 3, you did the curvature of of a path. You computed the curvature of a path. So if we have time, we're gonna talk about one of applications to physics, application of this parameterization of surfaces to physics, and that will be the curvature of surfaces. You may ask why this curvature of surfaces is useful. Well, it allows us actually to, in some sense, to classify between different surfaces. Okay. Like a very real life example. For example, the Earth, right? Earth it's a sphere. That's a surface, right? We live on a surface, the Earth. That's a two-dimensional space, and the Earth is not of course, it's not, it's a sphere. It's not flat, right? It's not flat thing, right? But if it's not, so it's not flat, right? So it has some curvature, and that's why, you know, when you look at the horizon, you know, it seems for you like the Earth would intersect the sky, right? That's the horizon, and that's because the Earth has some curvature. It's not flat, right? So yeah. Anyway, so I'm gonna talk about this like at the end of the semester, last lecture probably, as one of the applications of this parameterization of surfaces. Okay, well, I guess well. Anyway, time is over, I guess. So I didn't have time to go over even the first problem. Probably I was talking too much. All right, guys. Probably I'm gonna stop here. Next time, I'm gonna probably do the first problem. All right, and then we're gonna do the vector surface integral. Okay, guys. I'm gonna stop here. So next time, Tuesday next week. So next week, I'm gonna start the vector surface integral, and then, as I said, I'm gonna talk about reparameterization of surfaces, as we did for paths, and then Stokes and Gauss theorem. Stokes and Gauss divergence theorem. All right, guys. Thank you, everyone. And I guess I'm gonna stop recording now.